Good afternoon, everyone. I welcome you all to your day 4 of your international workshop on Introduction to Machine Learning and Deep Learning hands-on. And I welcome our resource person Subras Vain sir.
Hello. Hi.
And
Good
I
evening.
request sir to start the session.
Okay. So yeah, I mean, if you are waiting for me, like I joined at 6:30. I didn't.
Yes, sir. Yes, sir. I have seen.
Okay. Thank you.
Yes.
So I'll
Thank you,
share
sir.
my screen and yeah.
Yeah, I request all the participants to please mute yourself.
I hope my screen is visible.
Yes, sir. It is visible.
Uh, Give me some time to connect my tablet and. Hello everyone. Uh, let me welcome you to day 4 of this workshop on deep learning and machine learning. And today we'll be talking about transfer learning and all the other architectures of the deep neural CNNs. So let me share this screen. Yeah. So I hope you can access these notes now. Okay. So last session we sort of started talking in terms of CNNs, and we learned that how to represent images and how to sort of like how to represent black and white images and how to represent colored images, and sort of how to uh, 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 design the CNNs and how to process the images in say, the CNNs and do the classification. So until this part, if you have any doubts, you can ask me, or if there is something I said, I will tell you in the next class. please let me know now so that I can put that in my lecture later today. So before starting with CNN architectures, I just wanted to make sure that you got till this point where you know a little bit about CNNs and ANNs and how they work and how they can be used for image classification or any classification task. Even if you didn't get the ANN part as well, so let me know now. So I'll just give a quick recap of all those things and before going for the CNN architectures. Okay, great. So no doubts, but I will try to reiterate something before starting with salience. So, so initially we sort of started looking into this relationship of x and y. So the reason I'm trying to iterate this for like uh, for too many times because this is the core idea between ML and from this everything evolved. So we start sort of looking at like how given a number um, and its label uh, pairs, we sort of uh, trained a model using this, and using that model, we can predict any new data that is coming for any new data that is coming. Its label L new, and this is sort of we called as features, and this is sort of we call as labels, and this entire thing we called as data set, and and we divide the data set into train and test, and we trained with using this data set, and we tested our models using this data set, and when we see a new so that and we evaluated our performance using this test data set, so that when we see a new data, we can certainly predict its label accurately. And I saw and I said and it also argued that training a model is equivalent to predicting the function fx equals to y. So there is an underlying function for this data, and we're sort of approximating it. And neural network is the universal approximator, which can approximate any function given sufficient data for it. So, so sort of moving forward with this discussion, we saw that this y, this y is our label, and label can be kind of two types, or like two or three types. Like it can be yes or no, or it can be dead or alive, or it can be so one of the few classes. That is called a classification problem, where the label can be one of the few classes, and if it is a number, it is a prediction problem where we have an integer predicting the price of the house or price of everything. In the other hand, we saw that this x is an input to the model. So x is a feature and which we use as an input for the model, and this x can vary from task to task. The first task we discussed in the day one was to predict the price of the house, and we saw that to predict the price of the house, we require all the things that is necessary for predicting the price of a house, such that distance to school, distance to hospital, and all those things. And later in the day two, we saw that this X, we used a data set which was about uh, about Titanic survivors, and we saw that how these different factors such as sex and uh, class and age and gender sort of affected the affected the idea that if a man is dead or alive at the end of the journey. So we saw that this X can be anything, like it can be tabular, it can be one dimensional, it can be two dimensional. And yesterday we saw that this X can be a image as well. And later we will see that this X can be some text as well. And this X can be a text, and this X can be a audio signal as well. If you're using Alexa and all, the input to the text is a audio, input to the model is a audio, so the X can be a audio as well. So the branch of machine learning that uh, deals with the tasks where the input X is an image is called computer vision. And the branch of machine learning that deals with the all the studies when the input X is a text is called NLP, or the natural language processing. And these are the two major fields of deep learning or machine learning. And these fields have grown individually to a certain extent, such that it has now its own entire field, and you can sort of learn computer vision itself, and it will be a very big course for just computer vision. And then starting with X, we saw that starting with images, we saw that the image can be either 2D, which is black and white, or it can be 3D. These color images. So apart from that, we saw that how to represent this as a 2D tensor and how to represent this as a 3D tensor, and accordingly design convolutional layer to process that, and at last pass them to classification layers, or which I said fully connected layers, and or I mean to say ANN layers to pass it to the output layer for prediction. So this is the point where we stopped last class, and also did some codes as well. Please explain in the hands-on session today how to use the model for new data to get the output. So okay, so if so I'll just tell you. So what is new data? So for a model, new data which is something which it has not seen while training. So so just start thinking this as training a kid to ride a bicycle. So if you're training someone who is, so let's say like when a kid is like growing up, we just asked we just tell him or her that so this is a cow, this is a buffalo, and this is a dog. And when and let's say you have never came across a tiger in his entire life, and suddenly after some ages he's coming across a tiger, and he's finding it difficult to recognize the animal because he hasn't seen it yet. So the notion of new data for him is tiger, because during his training he have never seen a tiger in his entire life during his training. Here also, if during the training you are providing certain if during the training you are providing certain things as while training, if you're providing certain images as input and training the model, you're sort of saying that these are the things that means uh, these are things which we have labels for, and these are things have corresponding label as this. And when you are giving something called test data to it, the test data is itself a new data for the model. So if you want to train on certain data set, and you have suppose you have trained your model using a certain standard data set, and you want to do the prediction on on the picture that you have captured using your phone, then that's a different thing, because just have to format the picture in such a way that it can be sent as an input to the model. Once you do that, once the image that you are having with you for prediction is compatible with the model that you have trained, and you can put as an input, then you are good to go. Then you can make a prediction right away. So make sure that you will only ask the model where which you have already trained. So on the data you have already trained. So if you are training a model for cat and dog classification, you cannot show the model a picture of tiger and ask what it is, because it will always give you a probability score, because in the output layer there is 2 unit. So it will always give you a probability score between cat or dog. It doesn't have a unit for tiger, so it will never give a unit for tiger. If you show him a new cat image which which the model has not seen in his entire life, it can be able to make a prediction, because it is trained to recognize the pattern of a cat, not the not remember that okay, these pictures are of cat. So I guess you got my point there. uh, but I'll try to find a code block that takes JPG image or PNG image as input, and sort of. So what you need to do is that if you capture a PNG image, it will be either PNG or JPG, because these are the image compression techniques that our phone use to store a picture. So you have to convert it to in such a way that it can be represented as a matrix or tensor. Once you have tensor version of an image, then you can feed it to the model, and the model will give prediction. So this is the way we sort of see this tensor, and so this is the way we sort of see this uh, we sort of take the images that we capture in our phone and give a prediction. Any more questions? Okay. Krishna is saying, please repeat once again. So Krishna, could you please let me know which part I need to repeat? So I've been talking for 20 minutes. So if you could point out which part to repeat, 15 minutes, so I can repeat that, because this is the catch-up session, and I'll be happy to uh, like you know rewind everything that has been taught in the past 4 days, 3 days. Okay, so I'll repeat the model seeing the new data. This model can be applied to images processing technique, or we can apply them on numerical values too. Okay, So the CNN model is specifically designed for images. So CNN model is designed for images, but if you have number data, you can do 1D convolution, which is again a convolution. So the CNN is built on top of convolution operation. So the convolution operation can be done to images as well as numbers, but in practice, we generally we generally uh, do this for images. We do not use convolution for text data. But if you want, if you wish, we can use that. For that, we need to use the filter of size one dimensional. I'll just let you know in some time. I'm just addressing. Uh, Kausik is asking a question, I guess. Yeah. Okay, so I'll now repeat that, and I'll briefly tell about this the question that you asked about image processing and tabular data. Okay. So yeah. So what I was telling here is that uh, so the question was model C in new data. So when you are training the model, so the way I said yesterday, when you are training the model, what you're doing is that uh, suppose you have images like this, images and its corresponding level one, then image corresponding level two, up to let's say and level 1000. So let's say you have 1000 images and you want to train a model that can classify these images as cat or dog. Okay. So when you want to train a model using these images that can classify between cat and dog, then you need to find something called train test set and test set. So what you do, you took 80% of this data set, which is 800 data set for training, and you took 20% for testing. That is 200. So what you do is that you pass this 800 images to the model and you train. Once the model is trained, so you will get the model. So initially, what will happen is that you will randomly initialize the model, and then you will forward pass this 800 images. Then you backward pass it and update your gradients, and then you sort of then you update your gradients, and then you sort of uh, after updating the gradients, then you'll sort of get the new A's and B's. And after iterating this thing for let's say 100 or 10 times, you'll be able to get a good model. And once your model is trained, you can save this model, and you can use this model to predict this 200 images. That is called testing. And this testing, these 200 images are new. These 200 images are new for this model, right? So since this model are new for this model, uh, so these are this is same as making prediction on the new data. Okay. And so this is for the this is the way of, like, how we make prediction with the new data. So then I discussed that if you have an image on your phone and you want to classify it, let's say you captured a picture of a cat and you want to classify it cat or dog, so this image will be in PNG or JPG or JPEG, like that. So what you need to do is that you need to sort of find so you need to sort of convert this to tensor, because all these images that you see here are in tensors, PyTorch tensors, which you can load from Torch Vision that I discussed yesterday and use that directly. But if when you are seeing a new image, you need to convert it into a format so that it can be represented as a tensor, and you can pass this tensor to your model, and you can get the prediction of cat or dog. So I guess uh, this is clear to both of you for asking. And now I'll move to this now I'll move to this thing called 1D convolution. So when you have an image, so what the first step that you're doing is the convolution layer. In the convolution layer, I have a filter, let's say F1, and I am using this filter on this image. So what I'm doing is that I am taking this filter, I am putting it here, then getting some value out of it, V1. Then I am sliding this filter and putting it here, sliding this filter and putting it here, and so on. So in this way, I will be after completing the image, I will be getting. So I'll also go down here, and after completing the image, I will be getting another image, which will be whose dimension will be. So this will be smaller than the original image. So in this way, I am sort of reducing the dimension of the image. But if you see a tabular data, the tabular data will be of size like this, because it's just a bunch of numbers. So you can say it is like this. So you have a tabular data like this. So you cannot use a filter to filter out this. So what happens is that in tabular data, in some data, in time series data, time series where time is associated with every data point, what we use something called 1D convolution. The size is 1 cross 1, and we do that, we sort of parse it across this length to get a new vector. But that doesn't change the dimension of the data. The reason we do that, to generate this so capture this sequential feature. But in normal data, we generally don't use 1D computation at all. So I hope this is clear from my side, and more on this 1D convolution we'll see in the architectures that I'll discuss in this lecture today. I hope all your doubts are clear. So just let me know in the comments if it is clear or not. Yeah, clear. Thank you. So now I'll go to my uh, PPT that so what I will be doing today is that we'll be learning a lot of architectures. So what I discussed yesterday here in the day 3, we discussed that a basic CNN architecture, and we said that a basic CNN architecture will have, so if the input image is like this, we have a bunch of filters that will be applied on the images, and we'll get a, so for each filter will generate me a smaller image, and we'll sort of sandwich this smaller image to get a 3D smaller image, but 3D image in the second layer, and we'll apply value function, because we know that the image should be between 0 to 255, and this convolution operation might have uh, generated some negative value. So we sort of applied a value function, and you got a good positive valued block. And from this block we used max pool. Max pool is like taking a block and finding the maximum value in that block. And this max pool block do not affect the so the depth. So if the depth here is d, it will be d here too. So it did not affect the depth at all. So we saw that, and we applied a bunch of conv value pull, and so the pattern is, so when someone is saying I am adding a convolution layer, he is saying that I am adding a convolution layer, ReLU layer, and pull layer, because we do not apply just only convolution and leave that way, because we apply convolution, then ReLU, and then pull, and all these three things is called a convolution layer, and is termed as conv. And since it's the second convolution layer, it will be conv 2, and for this first, it will be conv 1, conv 1. Yeah. And with this, we sort of saw how we reduced the image to in such a small extent, so that we can extend this, we can sort of flatten this image now. And by flattening, we can sort of get a long vector, and that vector can be propagated forward to to the output layer, where the size of the output layer is 10. Give me 1 second. Yeah. I guess like I got my, yeah. So I was telling that, so we sort of saw that, uh, we sort of saw that we're doing that. But what happened, in so this was the convolution was developed in 1990s, and when people started thinking about reducing the size, because they didn't have any much compute power in their hand. But as the compute power grew, the size of image also grew. So it was very crucial to find out ways to train image classification models without like sort of worrying about how, like without sort of so 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 they sort of started creating more and more architecture uh, without worrying about the image size, because they reduced the image size to such an extent such that it can be trained using the existing technological advances in the GPU front and the computational front. So I'll be sharing my other screen, where I will discuss a lot of architecture that came from 1990s till 2016 and 17. So I don't include any recent models. So, but if you go for a complete computer vision course, there you can see all the recent model that started from 2018 till 2022. So when you in computer science or in artificial intelligence, the models that came from 2012 or even till 2016 and 17, we call that old, because the reason we call that old, because this field is growing very fast, and uh, the things that we discovered 5 6 years ago is also called as old. So I'll be taking you to another slide where I am using repurposing some of the slide that is used by uh, most of the famous courses in computer vision throughout the world, in from Stanford and from IITs. So I'll be using that, and I'll be, so since all these architectures are like very big and it is very hard to design, so I'll not be drawing them in this board, but rather I'll be showing you in the slide. I'm taking you to that screen. Yeah. So the history of CNN. So in the 1980s, they started this idea of CNN, where they sort of started saying about how uh, yeah, sort of started saying about how this convolution should be applied to the images, and how this convolution will change things for images by reducing its size. So if you see, here is the input pattern, whose name is named as UO or U0, and how then, so the initial names of convolution layer was uh, S cells, and they believe that they used these filters to extract features, and that's why they called feature extraction stage. And in the next stage, so they used pooling stage. So you might be thinking, like, uh, uh, as I said, the convolution block is consisting of convolution layer, ReLU layer, and pool layer. But here is only convolution and pooling. It is because the ReLU was invented in 2012. Before that, people were not using any ReLU method to sort of cancel out the negative terms out of it. So this is the history of CNN that we'll start learning today, and later I'll show you how simply you can code all these things, because since these things are so crucial in this ML domain, and this is so like uh, abundant in the ML domain, people have literally wrote code for every architecture that I'm going to discuss today. You can actually spend your time to write this architecture from scratch, but it's not a good idea in 2023 to write those architecture from scratch. If you're not, like, specializing in computer vision, I would not suggest that you shouldn't, like, go and write those big architectures, because the layers that I discussed yesterday had like 6 7 layers, but the layers that you will be seeing today is in the range of 100 and even 200 layers are there in recent architectures. So these big layers, like, we have to be very careful about how you write. So that's why I would suggest that, like, just use those architectures out of the box, and sort of use how you use the functionality that they are offering on this block. So coming to the our fast architecture, the fast architecture was proposed in 1989, and it was a continuous work, and it went till 1998, because a lot of concepts developed in this period, and also the handwritten digit dataset that I showed yesterday about the MNIST dataset was developed in this period, and Jan LeCun, who is a scientist and computer scientist, he sort of created this dataset of handwritten digits, and he used that digits dataset to sort of create this convolutional neural network that was able to predict the digits that is written on the image. So if you see the architecture that is that I'm presenting here, so input is an image, which is a black and white image, and so next next layer is convolution layer. And as you see, so they applied 5 cross 5 convolution, and with a stride of 1. So if you could remember, I mentioned that. So I mentioned that for an image you have to find certain filters. So let's say you find 10 filters, and each filter size is 5.5 5 plus 5. So in LeNet, they applied 5 plus 5 filter, and the notion of stride, as I discussed earlier, is that how much you want to shift. If you want to shift by one block to the right, so the stride is 1. If you want to skip this block and directly start at the third block, then the stride is 2. For instance, like, for instance, if, 1 second. your filter is here, and in the next iteration, you sort of move the filter by 2 blocks. Sort of, sound is not audible. Okay. Yeah. So if you sort of move the filter by 2 or 3 blocks, then the stride will be 3. But if you start from here, so if you let's say start from here and you just move by 1 block and place the second you just move the filter by just 1 block, then the stride is 1. So they applied a stride of 1 and they applied a convolution filter of 5 plus 5. And so apart from that, they use so after this convolution block, they used a pooling block for the size of convolution was 2 cross 2, and they applied a stride of 2 here. So the overall architecture is convolution layer, pool layer, convolution layer, pool layer, then FC. So when they got a very small enough image, they just expanded that image like so. You take these pixels and they just take this first row of pixels and put it here, and the second row of pixel, put it here, third row pixel, put it here, up to the last row of pixel, they put it here, so that they just flattened it. And after flattening, they allowed 2 fully converted content layer, and that will lead to the output. And this is the first architecture that he proposed. And the reason why there is no ReLU is that because ReLU was developed in 2012, and it is a Quark in 1998. So in 2012, so in 2010, image dataset, a new image dataset was created. So that is called LSVRC, which is large. This happening. I'll just test my. So it was large scale visual recog challenge. Okay, so this large scale visual recognition challenge was started in 2010 for benchmarking methods of image classification. And they sort of created 1 million images. 1 million is 10 lakh images. They sort of captured 10 lakh images of 1,000 different things. If you go to the LSVRC, this ImageNet website that I put here, I'll share this slide with you as well. So you can click this slide as well. So when I just clicked it, yeah. So this is the ImageNet website, and when you go to this site, you can see a huge number of objects are there. So we are sort of saying that given all this image picture, which is 1 million, and its size is large. So earlier we deal with 32 cross 32 image, but now the image size has grown up to 2 250 around. Not sure that exactly, the different images have different sizes, but around 250 cross 250. Yeah. So the images were very big. The number of images was 10 lakh. So as compared to the images that we saw yesterday, it has like 60,000 images. It had 6,000 images. So the number of images were also large, the size of images were also large, the number of classes were also large, like 1,000. So it's a very critical problem to learn and train the model on. So people sort of started exploring it because it was a challenge and people were given a large amount of money for that. That's why people from around the world started took this as a challenge, and they started sort of submitting the work to this competition, where they sort of started submitting different various model to achieve accuracy. So uh, I'll just show you like what are those models, and in a moment. And before going to show you what are the movements, models, I'll just briefly discuss about the cross entropy loss function. So I guess last time I said that I'll be discussing this cross entropy loss function, and by cross entropy loss function, what I meant is that this so uh, so so we sort of discussed about this mean square error, where I said that if your target variable is y and your prediction is y dash, just take a squared error. You can take a squared error and see the loss. So this sort of the loss. But when you have a classification task in your hand, so it is better to use cross entropy loss instead of MSE loss, because it sort of measures the entropy of the maximum likelihood of the uh, uh, prediction that we are doing. So the formula for that is pretty simple. It's just minus summation of yi log yi. So this measures so it will sort of find the uh, find the class which has the least entropy, and we can sort of say that this is the target class. So this loss function is generally used in for classification. It is a popular loss function classification, and we sort of here here is a special case of binary classification, where the y is 0 or 1. When the number of classes is 2, we call this binary classification, and when the number of classes is more than 2, we call it a multi-class classification. So this is just a loss function. I just introduced it here because I thought that it will be helpful for you to remember that we're doing a classification task, and the number of class will be 1,000. So also I discussed about the softmax activation function earlier. The softmax activation function we use when the number of values are more than 2. So let's say we are working on a classification job where the number of classes is 5, and we want to see which one is the winner. So what we did is that we sort of applied softmax activation on this vector, and we sort of got these values. And there the probability values, if you add all these things, you will end up in 1. Because see, uh, so this is 0.90 and 0.2, 0.5. So 0.2, 0.1, 0.3, 0.03, 0.03, 0.5, 0.08, and 0.08 plus 0.02 is 0.1, and 0.9 plus 0.1 is 1. So this certainly gives us a probability score for each class, and if you could mark, this is the predicted class, but the probability for that class is the highest. It's 90%. So this is the way we design the softmax function, and so softmax is used as the activation function in the last layer of the CNN for multi-class classification. Okay, so So, we'll start with the architectures that CNN has. So the architecture that CNN has started. Sorry, yeah, I think it was a mistake. we'll sort of now start with the architectures that people have proposed over the years. And since this ILSRV, sorry, LS, since this LVSRC, large scale visual recognition challenge, started in 2010. So from 2010, people started proposing different sort of models for this challenge. Okay. And in 2010 and 11, they used artificial neural network to do the prediction. So if you see clearly, so there is no point in like discussing those models because those are artificial neural network models. And now we'll uh, start to talk about the 2012 model, which is the fast CNN-based winner in this huge dataset. And this is the number that you see 28.2, 25.8 is the error rate that they make. I mean, if you if you show them a image of the 100 images of 100 new images from the data set in 2010 model, it was able to correctly classify only 72 models. So this is the error rate. How many images they sort of mispredicted or misclassified. So it was 28, and in 2011 it reduced to 25. In 2012, after using CNN, there was a huge drop in the model's error rate. It went down from 25 to 16. So out of 100 images, it made only 16 errors out of 100 images. And we'll see how what is the architecture of that. So this is the AlexNet architecture. So the overall architecture was similar to LeNet, but it was deeper with convolution layer, and it was stacked up on top of each other. And it was trained over 1.2 million images, which is around 12 lakh images with SGD, which is another optimization technique for updating the weights, the A's and B's, and yeah. So this was the winner of LSVRC 2012. So if I discuss this model clearly, so you see this part is the input image. So this is the input image. We see clearly the input image size was 224 cross 224 cross 3 because it was colored images. Then we sort of took a filter of size 11 cross 11, two filter of size 11 cross images 11, which produced two different uh, uh, different uh, images of size 55 cross 55 cross 48. Since they use 48 plus 48 filters, the depth of the second layer was 48. So they found this two set of different images, which which and they mentioned that they used different GPUs to train these two different uh, conv layer, and that's why it was done in parallel. So after doing that, so they sort of started. So after doing that, they sort of started putting max pooling layer on top of that, and ReLU was introduced in this. ReLU was introduced in this layer, but it is not explicitly mentioned there. So they created ReLU, and they put ReLU in along with the convolution layer. And in the second layer, they used a filter of 5 cross 5 as pooling, and they got the corresponding next layers. And by continuing like this, they sort of reached at a stage where they can expand these images because now the image has changed to 13 cross 13, and the depth is 128. So if you see, the size of image went from 224 cross 224 to 13 cross 13. And if you focus, the 13 plus 13 is a much smaller number, and on the upside, this 13 plus 13 image has all the information that was there in the 224 dimension, 224 cross 224 image. So I guess someone is trying to speak or getting his mic turned on. So yeah. So yeah, so this is the architecture they proposed in 2012, and it won the LSVRC with a very reduced amount of error rate. So if you see, this is the architecture that uh, this AlexNet had, and here is input image, and there is con plus pool, and then there is con plus pool. Then he applied a bunch of two only convolution layer, and then again a con plus pool. So if you go to the authors and ask why did you put it this way? Why didn't you put three convolution layer then one conv layer? So why didn't you put con plus pool and con plus pool, then only one convolution layer and then con plus pool and then full output? Or if I can do club this three as one and this two at one. So the answer to this question is pretty simple, because these architectures, so we know that convolution layer, pooling layer will reduce the size, but what what to what extent and how much do we need to reduce? All these things are experimental basis. So all these things depends on the experimentation. So the more experiment that you do, that then you will figure out which architecture is working for one data set and which architecture do not. So AlexNet has 8 layers in total, 5 convolution layers and 3 fully connected layers, and it was trained on ImageNet dataset, the dataset that I mentioned, LSCRC, and uh, max pooling only followed the first, second, and fifth convolution layer, and ReLU is the non-linearity that is applied on the output of the every layer. So all this layer, the ReLU is applied. So if you see this max pooling follow first, second, and the fifth convolution layer, but not on the third and fourth layer. Why they didn't follow? So they didn't mention. They just mentioned that we put max pool in this after these layers, and we skipped layer 3 and layer 4. So this is a calculation of how many parameters it had. So we saw that a total of 60 million parameters were used in this model. By parameters, I was saying, I mean to say is that the A's and B's that you saw. So when I was telling about backpropagation, I mentioned that you need to update the A or you need to update the B. So I mentioned to update the A and B just because that was one neuron, one layer neural network, and the number of parameters were only two, A and B. So once you make the network a bit deeper and make the network a bit bigger, so the number of parameter grows with it. And in AlexNet, we saw that the number of parameters in the convolutional layer was much smaller than in the fully connected layer. In fully connected layer, there are about 57 million parameters, and in all this convolution layer, it was only 3 million parameters. 3 million is pretty big, but as compared to 57 million, it was very small. And conversely, the time required to calculate the uh, uh, convolution layer outputs were much higher than the fully connected layer. Even if there were a lot of parameters to compute those parameters, you didn't need much time. But in convolution layer, as I mentioned earlier, you have to find a filter, and that filter, so you have to take a random filter, and that filter has to be put on the images, throughout the images by sliding. So you're doing a lot of computation on the images. And so you have like sort of put a lot of computation on the images, and you sort of you sort of put a less number of computation on the fully connected layer. So that's why the computational complexity in the initial layer of the AlexNet was much higher than the later layer. So it's just a the header specification where they mentioned they trained with SDD on two NVIDIA GTX 3 GB GPUs, and they took for a week to train. So I will code today and I'll show you. It's very easy now for us to train, and it will take very less time for our LexNet. And yeah, next on the list is our ZF Net. And ZF Net was the winner for 2013 competition. And similarly, so we have winner for 14, 15, and 16 and 17. So we'll discuss one by one, and I will let you know what are the new concept these model built in each year, and so that we are at a stage today where we can surpass the human level as well. So you see, so as humans, so when those people, when those competition guys, they took all a random 100 images and they sort of showed it to a human to classify it, if it is a dog or cat or bird or a bus or car or anything. The human made at least 5 out of 100 errors. So when they were presented with 100 images, they sort of they sort of were succeed by classifying 95 of them, and 5 of them were still misclassified. So they didn't classify it right correctly. But if you see, after 2015, these models sort of started surpassing the human level, because human is 5.1 and these models went below 5.1 to 3.6, 3, and later 2.3. If you see about ZFNet, so ZFNet is named after Zellier and Fergus, and they developed this model in 2010, and it was published in ECCB 2014. Yeah. 2014. So what it did is that it was the same as AlexNet. The difference was that the convolution layer that we saw in the AlexNet was a size of 11 cross 11, and uh, so it was changed from 11 cross 11 to 7 cross 7, and the stride was 4 and it was changed to 2. This is the only change they've made in the convolution layer 1. And in the convolution layer 3, 4, and 5, instead of this 384, 384, and 256 filters, they use a larger number of filters, which is like 512, 124, and 512 number of features. By doing this, they reduced the images to a much smaller extent, and they sort of uh, uh, reduced it to 6 cross 6 image. So if you see, it was then in the AlexNet it was 17, it was 13 plus 13 here at the end layer, and but in ZFNet they reduced the images to 6 cross 6, and 6 cross 6 is very small. To expand it to this ANN and start computation after that and classify that, and the error reduced from 16.4% to 11.7. There is a clear 4% drop in the error, and they sort of started uh, putting it in the competition, and they won the competition in 2013. So from this point, people, so the number of layers were 8 and 8 in both the models. Just the number of, so I was telling the other day that you please go to home and sort of start playing around with the hyperparameters. By hyperparameter, I meant the number of neurons, the number of neurons in a layer, the number of layers, the depth, and all these things. So see, in ZFNet in 2013, they only changed the changed the convolution size and also only changed the filter size, and they got a new model, and they are able to uh, get a uh, good competition out of it, also a paper out of it. So it just they just changed the hyperparameters and the model architecture. So, but in 2012 and 13, the number of layers were unchanged. It was still eight, even though they changed the filter size and all these things. The layer was not changed. It was still eight layers. But later in 2014 and 2014, there are two players. One was the winner, and one was a runners-up. And these 2014 people, the work in 2014, they sort of increased the layers. They went very deep, and they sort of improved from 8 layers to 19 and 22 layers. So if you see, the first network that we discussed was LeeNet, and LeeNet was had like 1, 2, 3, 4, 5, 6 layers. Yeah, had 6 layers. But in 2012 they improved it to 8 layers, and 13 it was still the same layer. In 14 they almost doubled or thrice it, the layer size, to 19 and 22. So we'll discuss now what are the models they created on 2014 and 2014, where there are two models, and one is the winner and one is the runners-up, and both the models were very good at reducing the performances, because it came down from 11.7 to 7.3, and the same year it came down to 6.7 as well. The error rate, it was near to human level performance, but was not human level performance. So I'll stop here and take some questions before proceeding with all the other architectures that is there in today's session. Please write your questions in the chat box, or if you have no doubt, you can just say understood, and I'll be moving forward in 2 minutes. Okay. Since there is no doubt, we can move on. If you don't have any doubts, please feel free to write that we understood, so that I would get a sense that you at least understood it, and I can move forward in that level. So next on the list is VGGNet, and this VGGNet came from this group in Oxford. They called a Visual Geometry Group, and this is the first time they started with multi-layer neural networks, where they sort of created a network of 11, 13, and 16 layers. And it's the first time they went very deep in architecture, which is like double or 2.5 times the earlier architectures. And they argued that, yeah, even 19 layers. And so it was a runners up in ILVS RC 2014. And so they argued that the reason AlexNet came over uh, were good over the LeeNet that was developed in 1990s, because they sort of increase the number of layers, the depth. So they argued that more layer means lead to more non-linearities, and depth of the network is a critical component for good performance. And second contribution that they made is that homogeneous architecture. Okay. And when they start started with this architecture, and they sort of got into the idea that they will like do the architecture homogeneous and make it more depth. And they began from this 3x3 convolution, and with a stride of one and padding of one, and then 2x2 max pool with a stride of two, and smaller, and also they started with smaller receptive field. So by receptive field, what I say is that so remember when I was uh, placing it, taking a filter and running it around the image. So what happens is that if the filter size is more, it will capture a lot of things in one filter. So that is called the receptive field. So receptive field of earlier models are big, but here they made it just 3x3 convolution, and with that, so they with that they sort of lower the receptive field, and they argued that less parameter will be faster. Also, this statement, they argued that two 3x3 convolution have same receptive field as a single 3x5 convolution, and three 3x3 convolution has the same receptive field as a single 7x6 convolution, but in terms of computation, it will be much faster. The 3x3 ones will be much faster. That's why they reduced the size, and they get they get all these things in return. And Vision 19 only slightly better than Vision 16, and yeah, so this is the comparison between the VisiNet and the AlexNet. So you can look at this chart, AlexNet versus VisiNet, and in terms of memory and in terms of parameters. You can see VisiNet was heavy in memory as well as parameters than AlexNet, but it was better in terms of the it is better than the earlier architecture. Okay, so this was the VDSnet all about, and yeah, now we'll move to the next uh, winner. So this was the runners-up in 2014. So we'll now move to the next winner, that is Google Net. And so this was the winner with a 22 layers, and it was uh, proposed by this guy from Google. And yeah, so we'll see the Google Net now. Okay. So when we started seeing about, when we started with Google Net, Google Net uh, started with another ideology. Uh, so first thing is that just like VDSnet, they made their network deeper, and they wanted to reduce the parameter count, reduce the memory usage, and reduce the computation. There are 22 layers I already mentioned, and they didn't have any ANN layers or FC layers, and uh, they, they introduced this inception module to their network, and they introduced only 5 million parameters, which was 12x less than AlexNet. So AlexNet had 61 million parameters, but if you say inception net, it had only 5 million parameters, and it won the IL SVRC competition with 6.7% error rate, and yeah. So now I'll talk about this inception model. So this introduction of this inception model in this CNN made it more faster, more efficient in terms of memory, and more efficient in terms of parameter as well. It also made the winner. So if you see this inception block, so what we learned earlier is that to use a convolution filter of size 7, or AlexNet use of size 11. In our task yesterday, we used a size of 5. So there is this notion of deciding which convolution size to use while working with a CNN. The guys at Google, they said that why should we care about which convolution to use? What we can do is that we can just apply all the fundamental size of convolution and see which one is performing better among them. And the model can decide itself which one to use and which path to not. What they did is that they put this inception model, and what inception model does is that it passed the image to all these convolutions, and all these outputs were recollected and concatenated at the top. Again, this will be passed to another inception block where convolution of different sizes will be applied to it, and later stage it will be concatenated. So uh, so yeah, so what they did is that, so while computing this, all these four things were computed parallelly, and it was merged with uh, it was merged with um, uh, merged. It was concatenated after this computation. So they used multiple receptive field sizes of 1 cross 1, 3 cross 3, and 5 cross 5. and a pooling size of 3 cross 3 was used. So what is the problem with this? The problem that they faced with this was, uh, so since earlier they used to have one convolution layer 3 cross 3, so now we have 3 cross 3 and 5 cross 5 and 5 cross 5 and 1 cross 1. So the reason, so what happened with this setting was that they sort of increased, they sort of saw an increase in the uh, uh, computational duration, and also it was not computational very expensive to add all the different size of filter to the same image. Earlier we were only adding one size of filter. So to tackle this problem, what they did is that they introduced something called 1 cross 1 bottleneck layer, or 1 cross 1 filters. What you saw here is that here is the image of 56 cross 56 cross 64. Okay, so let's say there is an output from an intermediate layer where where the image is of the size 56 cross 56 cross 64. So what will happen if you apply a 1 cross 1 convolution layer with 32 filters? So I'll just take you to the note page, and so like how this will affect uh, the size of the image. So let's say you had an image of 32 cross 32 cross 3, and you applied a filter of, let's say, 3 cross 3. In the resultant, you will be getting, uh, 1 second. There is a formula. Yeah, it was W n minus k plus 2. Okay. So this is a formula that we'll be using to find the resultant image size. So n is this 32, k is the filter size, so it is 3, p is the padding size, is 0, x is the stride size, which is equal to 1. So we'll put all these values into this formula to find out if there is an input image of size 32 cross 32 into 3, and output, and there is a filter of size 3 cross 3, what will be the output? 3 cross 3 cross 3, 3 cross 3 cross 3, and we assume that the depth of the filter is same as depth of the image, because you have to design it in that way, because you have to cancel that out, the depth out for one filter. So the output in this case would be 32 minus k, with 3, plus 2p. 2 into 0 is 0, by 1 is plus 1 is equal to 30. So you'll get a image of 30 cross 30. So you converted 32 cross 32 cross 3 to an image of 30 cross 30 with filter number 1. Similarly, with filter number 2, we will also get 30 cross 30. Let's say you have 32 filters. Now we'll, with filter number 32, you will make it to 30 cross 30. So if you club all these things, you'll get an image of size, you'll get a 3D image of size 30 cross 30, and the depth will be 32. Okay. 30 cross 30, and the depth will be 32. So, but what will happen? What will happen? Let's just think. So, let's say this is 30 cross 32, 30 cross 32. So now you have an image whose size is 30, 30, and the depth is 32. And you sort of, instead of applying any 3 cross 3 or 5 cross 5 filter, you sort of try to apply a 1 cross 1 filter. And the depth is, of course, 32, because the size of the depth of filter, the height and width of filter will be much smaller than the image, but the depth of filter will always be same as the depth of filter will always be same as the depth of the image. So what will happen if you put this 1 cross 1 filter on this 30 cross 32 cross 32 image? So if you could compute it from your side using this formula, and let me know what will be the output size of this image using this formula, where n is the dimension of input size, and k is the dimension of filter, and p is the size of padding, which is 0 here, and s is the size of stride, which is 1 here. So if you could compute that and put it in the chat, what will be the dimension of this resultant image when applied with, so size of image is 30 cross 30 cross 32, and filter size is 1 cross 1 cross 32. And the formula is n minus k plus 2p by s whole plus 1. Just try and put the in the chat what will be the output of this.
Hello. Hello.
Okay, so we'll do the calculation now. The n is 30, the k is 1, p is 0, Let's try this one. And we add 1 to that, which is 29 plus 0 by 1 plus 1, which is 30. So you see, now the image that whose size was 30 cross 30 cross 32 now changed to 30 cross 30 cross 1. So this is for filter number 1. And if you apply multiple filters till f set 10, you'll get corresponding 30 cross 30 cross 1 images, and you can club them to make another 3D image whose shape will be 30 cross 30, and instead of 32 now it will be 10 now. So what we saw here is that this 1D convolution do not actually change the dimension of the image, but it only can affect the dense of the image. So let's say the dense was 30 cross 30 cross 32, it is now reduced to 30 cross 32 cross 10. The dense reduced from 32 to 10. So this was the real motivation behind introducing 1 cross 1 convolution in the scene. I'll take you to that screen now. Now you can see the image was 56 cross 56 cross 64. But after applying 1D convolution with 32 filters, they now reduce it to 32 dense of 32. So now, if the number of channel is decreasing, the computational power that is needed for this image to half the channels is also decreasing, and so that's why the the problem that we're having here, computationally very expensive, is now resolved because we found a way to reduce the dimension of the image in the intermediate layer while maintaining its height and width. So they did that. It preserves the spatial dimensions but reduces the depth. So it projects depth to a lower dimension, yeah. So instead of using in the left hand side a picture here, left hand side picture here, here. Whatever. Yeah, here they started using convolution, 1D convolution with this intermediate layer, so that when they get an image from the previous layer, the 1D convolution layer will decrease the dimension of it, and that lowered dimension image can be passed now to the next layer to sort of making it computationally more effective than the first model. So this is the with dimensional reduction. So in this way, they are able to make the model less complex and also make the model less computationally effective. So this is the full architecture of Google Net, and the final layer where the prediction is happening. This is the intermediate layer, and this is the classifier output. And also they had auxiliary layers. So auxiliary output layer. So what I'll just tell you what an auxiliary output means. And before that, yeah. So before that, let me tell you like the concept of vanishing gradients like um, or yeah, vanishing gradients. So what happens in a very deep convolutional layer, when you back propagate the gradients to update the A's and B's or the weights, so the factor you're updating vanishes with the depth. So the gradient becomes so small, even if you do a updation to your weight or updation to your yeah, updation to your weight or updation to your this parameters. So it started great here in the initial layer, and it started falling apart when you go deeper. So it's become so small that the updation doesn't mean anything. If the earlier weight was 1.5, it will be like 1.50001. So so that small changes is not very effective for learning a good model. That's why what you do is that you sort of put output layers from the intermediate layer such that these output layers can be so gradient from here will flow, from here also flow, and from here also flow. So at this point you will find gradient coming from this point, you'll find gradient coming from here as well as from here. So even if this one is vanished to somewhat, this one gradient coming from this output layer will still be there to make it a valid change in the weights of A's and B's, or you can say the parameter. So this was the idea behind introducing auxiliary layers in the CNN, where instead of having one output layer, you sort of have multiple output layers coming from in between, so that they are able to retain the gradient value to big enough to make a valid or to make a significant change in the gradient. So with this, here comes the end of GoogleNet. Before moving forward with other architectures, I would I wait here to take some questions regarding VGNet and GoogleNet, and I'll be happy to explain if you want it. Yeah, yeah. Now we'll go to the deeper layers, where the layer size increased from 20 to 150 to 150s, like that. And also with this deeper layer, people are able to achieve performance that is better than humans. So I'll just take one moment for waiting for questions in the chat. So if you are really there and uh, if you want to have questions, you can ask in the chat. Okay, so we'll start with the deeper ones. So we have not much time left with us, so we need to complete these ones. And so before starting the deeper layers, so some people can ask like, so how deep can we go? Like how deep, how the layers, what, like, how deep can a, like, neural network grow? So what happens when we continue, like, stacking layers, deeper layers on a plain convolutional neural network? So it's like 20 layers and 56 layers, and you can see the uh, the training error reduces better. Uh, yeah, the training error. Yeah, at any iteration, the training error is lower than this 56 layer. Uh, yeah, so we saw that this in so if you like to read any graph, what you can do is that you can just put, draw a line, and see these 2 points. And here we saw that the deeper layers are performing worse than the shallow model, because at any point the training error or the test error is lower is better. So if you see, so if you have less training error, your model is performing better. But if you see at this instant, this point is performing better than the uh, 56 layer model. Uh, so so you see that uh, so there is a concept of underfitting and overfitting. So if I can reiterate, so if I can just define those two terms. So overfitting is something. So let's say you are training a model for classifying cats and dogs, and let's say you give a lot of data of cat and a lot of data of dog. So what do you want the in the ML model to classify cat and dog? It should capture all the essential features of cat and all the essential features of dog, so that whenever it sees a cat, it should look for those features. Such as when you are looking at a cat, where we can say that it is a cat because we can see the fur, we can see the mustache, we can see the way it sounds, or we can see the way it works, and we can confirm that it is a cat. So these are its features, and we want the model to know these features, like to model these features inside it. But what will happen if we show the model all the cats that is there in this world? So in that way, the model will remember that, okay, these are the cats that is in the world. But as compared to humans, if we see a cat in our home, then if we are shown with any wild cats or any cats from any other country which may be visually different, we can still say that it is a cat, not a dog. But if you go for the models, if you train it with a smaller number of cat models, it won't be able to say if it sees a new type of cat from Europe or from America. So so the so the problem here is that you should train the model in such a way that it can only it should only capture the structure of the cat, not the entire cat. But because if you give all the cat images that is there in the world and ask the model to learn from it, the model will just remember that, okay, these are the images of cat. So we do not want that. That is called overfitting. We are just fitting the model too much. And in contrast, the term underfitting is something we sort of find if the number of data is very less. So so let's say we need to see at least 10 cats to know that, okay, this is the structure of cat. But what if we just only have picture of 5 cats? Then there is not enough data to sort of capture the structure of the cat in our model. That is called underfitting. So what I saw here is that the deeper the model we grow, the more complex it becomes. And to train a complex model, we need more data. So since the data is fixed, the deep model is actually underfitting since it also performs worse than the standard model on the training set. So why it is underfitting in the shallow model, in the deep model? It is underfitting in the deep model because the deep models are very deep, and as I said, this the problem of vanishing and exploding gradients. So it is just an explanation of what I said about vanishing and exploding gradients. Um, the gradient that we are backpropagating and that we are using for updating the A's and B's or the weights or parameters keep getting reduced for each layer, and so that after some layers it will reduce to very small value, and it will not affect, so it will not be effective updation against the uh, in the model. So this is the vanishing gradient and exploding gradient concept, where in the exploding gradients, the gradients grow very fast to uh, sort of like update it more. So it is also a problem. We just want the gradient updation to be just right. Looking at this problem in 2015, people have proposed RESTnet. The RESTnet is uh, the RESTnet tells that the deeper model should be able to perform at least as well as a shallower model. So the solution they proposed is something called skip connection. So the skip connection means, so they will connect the input layer to convolution layer and this convolution layer to another convolution layer, and the output will be coming from this convolution layer. As well as this connection, they will also connect the X directly to the output. So it's like not having this two layer in between. The input will flow from this point to this point without crossing this two. So one part will cross this network, and another part will skip this network and go directly to this point. So what is the advantage of it? The advantage of this is, so remember what I said about vanishing gradient. So vanishing gradient, so if you start flowing the gradient from this point till the end, so it will vanish, right? So what if you flow the gradient from this point till here, and it will go through this layer. Also, there will be an alternative gradient that will flow directly to this layer, and it will be added to this one. So let's say here the gradient reduced to 0.02, but the gradient that came from 0.02, but the gradient that came from this in this path, in this curve path, will still be the gradient that is here. So let's say the gradient at this point is 0.2, and if you see, the gradient is now decreased in this iteration, but since you have managed to add a connection from this point to this point, the gradient now sums up to 0.2 plus 0.02, which is 0.22. Now we're able to capture the gradient and also preserve the gradient and do not let it to vanish or explode. This sort of block is called residual block. And in ResNet, they added a lot of residual block to design a very deep network, which is 153 in length. So they proposed sort of four uh, ResNet models. The first one is of size 34. The second one was of size 50. The third one was of size like 101, which is huge. And of course, the fourth one was 152 layers. So this is the theory behind ResNet. that they proposed, and so ResNet was like got along with ILSERC, it performed better in all uh, 5 different challenges, which include like image classification, image detection, image localization, and so Coco is another dataset, and it sort of surpasses everything. So still till today, people use ResNet to benchmark their work. ResNet was one of the greatest contribution of of the last decade, where they sort of uh, won many awards in 2015. So uh, uh, so with this, we have ended our presentation on all the classical models, not classical, I would say the basic CNN models, and I will be using PyTorch to code them all. And so the proposal that came afterwards did not improve much on the ResNet. So we'll not discuss that. And also the number of layers stopped at 152 at that point. And after 2017, we can see a lot of new convolutional layers that are proposed in the last 5 years from 2018 to till today. So we'll not be discussing those layers. If you take a very focused computer vision class, you'll be able to find those models there. And so we'll not discuss those models now. Uh, so with that, today's theory lesson is done. So I just want to do one more theory thing that is called transfer learning. So we'll do that after the break. So already 2 hours has been gone, and we'll do the transfer learning part after the break. So meet you after the break after 10 minutes. Uh, thank you. Hello, welcome back again. And yeah, great. So we'll now be running some codes, and we'll be seeing how this model works in real life and code. So let me share you the code screen now. Yeah. So if you I'll this share this notebook with you guys, and Krishna is asking, there is no link for the recorded videos. I think ma'am will upload these to the drive, sorry, the YouTube, and um, she will share the link. So I have shared the Google Colab notebook link. So just go to that notebook, and I showed how to change the runtime from CPU to GPU. Please do that, and please write in the comment if you have done that. So I'll help you if you couldn't get the GPU running. So please try, and please reach back to me on the chat. Then I can start. Got one reply. Okay, attendance. Yeah. So if you can access this notebook and turned on the collab, so kindly reach back to me. So if you guys got the collab link and you opened it, and you must be seeing this page, and then you should go to this runtime tab where you go to change runtime type, and here in the accelerator there must be none. You have to select GPU and then hit save. It will change the runtime for you, and you will be able to access the GPUs for you. So if you go to yesterday's code, you can see that we trained the, so we tried training a model for we tried training a model for Cypher 10. So if I Google that, Cypher 10 is a model, is a data set of all these things: airplane, automobile, bird, cat, deer, and all these things. And it's a data set of colored images. It's a 32 cross 32 cross 3 cross 3 size image. So when I trained it using ANN, which is not a good idea for image, so we need to train it using CNN. So when we try training it using ANN, we got a performance of 51.99, which is not good. So what we did here is that we sort of tried training the same data set with a CNN model. So I designed the CNN model here. You can see the architecture here. So it's like there is one convolution layer, so two convolution layer, one pooling layer, and two FC layer. So it's just a random convolutional neural network. And so what we did is that we applied this conv relu pull like 2 times on the input. Then we flatten it to get the larger dimensional vector, and we then applied one fully converted layer and one output layer to get the output. So it's just the code that is written for creating this image, but you can change it accordingly to change the dimension and change the sort of architecture. So the way we proceed yesterday as well is that we load the dataset using the PyTorch Torch Vision Torch Vision library, and it's the same thing that the code that we loaded yesterday. So we loaded that, and we created the data loaders, because we after downloading the dataset we need something to load it from the memory, and we're using data loaders which are specifically designed for loading images. And we did that, and we so after doing that, where our data loaders are ready, then we created the model by creating the object of this class, CNN class here, to defined here. And remember I told you yesterday that how to move your model to the GPU. So we're doing, so where all we did is that we just did .to device, and it is now in the GPU. And we defined our loss, which is the cross entropy loss. If you remember, I discussed today also, for classification we need to use cross entropy loss. We use cross entropy loss, and we use this optimizer, and this is the common optimizer you can see in any task. And then we wrote our training loop. So if you see, now your model is in the device or in the GPU, and also while loading the images, so you are also putting images to the devices, images and labels to the device as well, which is the GPU. And all this line is same in every case that we have seen till day one. So this is the same, and this is just like forward passing, calculating the loss, backward passing, and taking a step, or also operating the weights. Then there's a little print statement for printing. So what I'll do is that I'll just take each block and put in one shell, and I'll start running it one by one. So this is CNN for Cypher 10. And first we need to import all these things. Let me stop this run. Okay, let me keep this running. Let me create a new notebook and start running there. So there is a program running here, so I don't want to uh, um, stop it. So it's the name is day not so day 4.2. Yeah. Let me put the text here, and text here is CNN for 5.10 to that, and we put the code for importing all these things. We got the allocation, and we now need to define the model there. So I don't think they will give a lot more of GPUs for one user, but let me try to get a GPU here as well. Okay, there. Okay, it's not allowing me to use GPU in multiple sessions. So let me delete this notebook. I don't think this notebook is of no use. Okay, let's just delete that, and let me see till what point this run has gone. Okay, let me stop this run. Okay, great. So let me start putting my codes here, one after the other. And here we have already connected to the GPU. So if I put this code here, and if we print the device, you can see it is CUDA. It is CUDA. Okay. Then we take a block to define the model. So make sure to follow along with me on your respective notebooks. So if we define the model, and we load the data set. We download the data set, and since I have already downloaded the data set, it will just show that it is already downloaded and verified. If you go to this file folder and this data folder, you can see Cypher 10 dataset is already here. Okay, great. Then we'll create the data loaders. The data loaders sort of help me to load the image data from the files and make it work in this program. So I have created the data loaders. Now I need to define, so I have to initialize the model and define the loss function and the optimizer. It's the same for all the models that we have designed. So we did that as well. Now let me go to the training loop and run that. So this is a training loop. You'll train the model. Meanwhile, when it trains, let me also see. So actually I ran it already, and let's just wait for this code to run. And meanwhile, if you're facing any problem running this notebook at your end, you can put it in the comment. I'll I'll resolve if you cannot activate the GPU, or if you cannot you're not getting any output or getting any error. You can put in the chat while this model is getting trained. It's gonna take a while to train. So now the training has been done, and training has been done for 10 epochs, and the loss reduced from 1.2 to 0.06, which is like a 100% reduction in the loss. Let's just evaluate and see how many all out of all the test examples did we get right this time. Yeah, as you can see, the test accuracy is 73.38%. I just highlight this, that test accuracy is 73.38% just by changing ANN to CNN. As you can remember, I showed the with the same data set, we designed an ANN and the accuracy was 51, which is like 22% worse than this. And if we sort of start to design better and better CNN, we can take this accuracy up to 85 or 86 as well. So which is the next thing in our mind. So we'll try to improve this accuracy by sort of creating by sort of using different models that we have learned today. So to do that, let me write a text block saying additional CNNs for cipher 10. Additional CNNs for cipher 10. Okay, so let me again take this load blocks and put them individually on the slides, and also making sure the device is available as CUDA. So I don't need to do this all the time, but it's nice to see because this code is completely different what we wrote before. Okay, defining the transformation, creating the batch products, and everything is exactly same that we developed earlier. Okay, so now as we are here to run the model, to run the to run this like uh, this, I'm using 4 models today. One is AlexNet, one is VGGNet, one is GoogleNet or the InceptionNet, and one is ResNet. So the 4 models that we learned today, the 4 major models, I'll be trying that, and I'll be I'll be showing you how easy it is to train these models in this day, because it takes very less effort to train this. Before moving forward, let me introduce you guys to the concept of transfer learning. Okay. So let's say when we're teaching a kid, so we're not sort of showing the kid every pictures or every images that is possible. So once the kid start learning this like how a round shape means, what say straight line means, we sort of then don't teach it again and again. So we assume that, so it will be difficult for him to, like, look at an animal or look at a bird and sort of identify that. But once the kid grows, it's sort of very easy for him to, like, see animal and identify, okay, this is the animal. So like, even if we are growing older and we are traveling away from our home, we get to see a lot of new animals of that reason. So, but we do not require that much of guidance, assistance, but what we are doing, what we generally requiring in our childhood. So the concept of transfer learning begins when people started to question how this convolutional and pooling layer is sort of uh, identifying these objects. So image classification is a complex task. How this convolution layers and sort of this pooling layers is deciding what it is inside an image. And they found that also some intuition said that. So suppose there is image, and image is going through a lot of conrelu pool layers, the CRP layers. Before going to this fully connected layer, where it is connected to the output layer. So they say that given an image, these initial blocks will try to learn all these features which are there, in all the images, like straight lines, shape, curves, like certain shape, rounds, and all these things. So it will be there in all the images. So once we go deeper in our uh, network, some layer will try to find fur in a cat. Some layer will try to find tail in a dog. Some layer will try to find the eyes of a cat or eyes of a dog. So now the features are more specific to class rather than it is specific, rather than it is general across all the classes. So when we go deeper, so we'll be able to figure out these specific features of classes rather than more general features. So they said that if you train a model, so they said if you train a model using any data set, then these initial layers can be repurposed. Because so let's say I train my model using ImageNet dataset. The dataset that we discussed with 1.2 million images is called ImageNet. ImageNet. So ImageNet, since ImageNet is a collection of a wide variety of objects, so they say that if you have trained a model using ImageNet, it's high probability that all the functions of that ImageNet, all the let me run this code first because it will take a time. Take time to run this code. Let me run this code first, then I will start explaining the transfer learning for you. Okay. So I was at like so 1.2 million parameters in the ImageNet. So they say that ImageNet is a data set that consists of a lot of this lot of this uh, images, which is very diverse. And since the images are very diverse, and it is very so since the images are very diverse, and it has a lot of diversity in it, so it's crucial to know that if a model is trained with this ImageNet data set, it will capture all the things that is there in an image, or all the things that we see in a real world. So they say that since initial layer captures, so these layers will capture all the basic shapes, and these basic shapes are coming from a diverse range of uh, objects. So it is better to repurpose these layers for other classification tasks as well. So for example, you have a network model that classify cats and dogs, and you train this model and you saved this model with you. Now you have the weights of this model. Now you can, so you spend you spend so the reason behind, like, saving and repurposing is that because to train a model in today's scenario, when the deeper network has came, it's very expensive. You cannot really take a it's very hard for a normal uh, person to take a model, so to take a data set and create a larger model and train it from scratch. It will take a lot of time, and also to get the good performance, you need to tweak the architecture a lot. So to handle that issue, people started looking at a way to repurpose uh, uh, the model that they had earlier for the task they have in their hand. So to do that, let's say this model M1, they trained using cats and dogs, and let's say they want to repurpose. So let's say now they have to classify between tigers and lions. So instead of training a model M2, what they will do is that they will just take M1. Since M1 is trained with all these cats and dogs, so it must have this uh, features that is very basic for an animal in the initial layers, in these layers. So what they do is that they just they chop this model into two, they discard this part, they keep this part, and instead of this, they fit another layer which will learn all the specific stuffs to lions and the tigers. And they do that, and they don't train this part. They freeze this part, they only train this part. So the resultant model will be like this. This is M1, this is M2. Together I can say M12, which is much smaller than creating a new M2, because now this part will not be trained. Not trained. It will not be trained. It will be frozen, because this part has already captured some features that correspond to all these things. Okay, so so if you sort of like got the idea from this point, uh, so we don't really need an entirely new model for our new task. So you can just repurpose an existing model to use it in our advantage. This sort of learning is called transfer learning, where we are transferring the knowledge that we got from one task to a different task. So this is case one, and let's say case two is something where the input. So the model that you have in your hand has number of classes 2, dogs and cat. But now you want to classify 3 things: lion, tiger, and let's say bear. So what will you do now? So now what you can do, the model will stay same. In the last layer, it will be changed to a larger number of layers. There's already 2 here. You remove this part and you put another part here where this will be new, and output size will be equal to 3. Okay. So also here you need to make a decision how much layer to spare and how much layer to like keep. So if you see, if you have a task, if you train the model with cat and dog, now you are getting a new task of classifying lions and tigers. So you can see the cat is very similar to tiger, and the lion is kind of like looks like dogs as well. So it's okay to chop off almost all the layers except the last layers to accommodate the new features. But if you see, if your task in hand is like so if you had dog and cat trained with your older model, and now let's say you want to classify, let's say, types of birds, crow and pigeons. So it will be very hard. It will be very hard for you to capture those features that is there in a bird in the earlier layers of the cat and dog classifier. So in that case, so if diverse task. So in that case, if your model is like this, then then you can just, then you can chop in the middle, or go back to up to 4 or 5 layers. So you have the freedom now, because you know, so this initial layers will be only capturing shapes and all, but furs and beak and will not be captured by this cat and dog classifier. So you have to repurpose that. So this ends the discussion of this transfer learning. But so if you have any doubts regarding transfer learning, you can reach back to me right now. I'll be happy to clarify your doubts. So can we see the output in form of image? Yes, we can see that, but I haven't put any visualization code in my notebook. So for now, I don't think I can show you, but so I'll make sure to, so actually I can show you just one image, but I'll make sure to put code for visualizing these images in the notebook. If you have the notebook, you will get the code tomorrow. You can recheck the notebook, and so you'll have the code tomorrow. Because I'll make sure to put, like, so this is the image and this is the prediction. If this is the image, this is the prediction. I can do that. So that will take some time, because you have to find the labels and for the corresponding image, and then sort of join that to, so in that form. But uh, now I'll not do that. So I'll put it in the notebook. You can find it in the notebook if you open it tomorrow morning. We'll use matplotlib for that. So yeah, if you have any other doubts, you can ask. So the code is running, and I don't think I'll be able to complete this code run, because it will take a lot of time to run. But I will go through the technique that I'm trying to, like, pose here. So you see, the training with new models is just same as older models. It's like you import all these things, you create the data set and data loader, and then you write a function for the training loop. Is the same as the earlier. This 4 lines is same, like you, for image and labels in train loaders. So it just, if you make a train loader, it will be just like a Python for loop. So you're just extracting images and labels from the train loader, and you're sending these images and labels to device. And then this first step is same in all the thing that I've told, right, till that. So it's like the optimizer, we are making it 0, and then we are passing the images to the model, and which is the forward pass, and you're sort of getting the loss out of it, and then we're back propagating that loss, and we're updating your weights in this optimizer.step. So do that, and you do the printing of all these things in for each epochs. Okay, so this is the function for training the model. Then we have this code for evaluating the model. So for evaluating the model, you just have to load the data set, this test loader, and send the model to, and send the images and labels to this device, and we get the output, and we sort of find the accuracy out of it. So I did ran the AlexNet one. So what you need to do for AlexNet is that, what you need to do while transfer learning. So you see this torch vision that I imported here. Yeah, here. So this torch vision dot models as models. So if you go to torch vision models, so if you go to this page, I'll just share this page. If you go to this page, you can see the every model with every state-of-the-art model that is defined for image classification is in this page. So you see, yeah, AlexNet, ConNext, DenseNet, EfficientNet, GoogleNet, InceptionNet, VGZNet, and everything. So recently, there is a rise in transformers, vision transformers. Vision transformers is also here, and everything you can find, and all those weights are there. So all those models are there. So what these people have done is that they have uh, they have coded all these models, and they have trained these models using ImageNet. And since ImageNet is a diverse variety of image, the image contains a diverse variety of image. It will contain everything, like the animals, birds, and then automobiles, then vehicles and airplanes, man, and everything. So since the ImageNet is it has contained everything, So these models have a knowledge of, like, a very good knowledge of the real world. So they have trained on the shapes and the size and the features of all the real world images and all the real world objects that you see in the daily life. So if you take, so, and these are all trained, these are not like, raw models, these are all trained, and they are very well trained on these data sets. So they possess the power of, like, capturing the features of all these objects that we see in our real life. So what happens is that, so what we need to do now is that we just load these models. So download these models, available for free. We can download these models. We can chop the front part of this model and put our, front part on top of it, so which will train for our data. And so we'll freeze the rest of the model, so that it won't get trained, and also our training will be faster. And we'll do that, and we'll do that too, and we'll do that, and do that for our model, and so that we can train this model, and so that we can repurpose the trained model for our benefit. So the first model that I trained was AlexNet. Please share the quiz links. Quiz has not started, so the quiz will start in after some time. The ma'am will tell, but there's a code. I'm just going through the code walkthrough, so bear with me. Give me 1 minute. Okay, so okay, so what I need to do is that we need to train this. So this is taking a way lot of time than it should take. Let me add a line. This, yeah. So what we do is that we sort of take this VGG 16 model. So I mentioned that VGG has like a fewer so like 4 models. One is 15, like 10, like 6, 16, 19, 23 or something. But yeah, so we're using the 16 VGG 16 architecture. And what we're doing is that we are sort of I got a comment. As a train model function has 4 parameters, but you call only 3 parameters. Where? Okay, train model has, okay. The number of epochs has a default value of 10. So if I do not pass anything, it will take us 10. So that's why I didn't pass anything in the fourth as a fourth argument. Okay, great, thank you. So you can, if you pass a value that is not 10, it will be modified. If you do not pass any value, it will be same as 10. Okay. So, so in transfer learning, what you do is that we loaded this model and we kept pre-trained equals to true. So if we put pre-trained equals to true, what it will do is that it will download the pre-trained model. It will download the model which is trained using uh, all these ImageNet data set, and it will try to download those model. So so one way to, like, freeze. So I if you could remember, I told that we have to freeze the model in the initial part, and we have to sort of unfreeze in the end layer to get it trained. So for that, I added this line. So for parameters, so we need to freeze the parameter. We don't want the parameters to update. So for parameters in all these section parameters, we sort of set this requires grad uh, uh, requires grad like this member to false. So when we said that, so it do not require gradient now. So the gradient won't be coming to this parameters and operating there. So we froze that. So we froze for every layer. So after freezing it for every layer, what we did is that we went to the last layer and we changed the dimension of the output layer. The output, so this is the second last layer, and it is the output layer. The output layer size has now reduced from 1000, because there were 1000 classes. Now it is reduced from 1000 to only 10. So why 10? Because the task that we have in hand now is called Cypher 10, and Cypher 10 has like 10 classes. Since Cypher 10 has 10 classes, the output layer will also be 10. So we did that, and so this is just the loss and this is the optimizer, and we started training the model. And also we called the evaluate model method here to give the evaluation score for VGC 16. So this is going to take a while to run, and so also so for that, so while it is running, I'll just show you what to do with the others. So the Google Net has also similar setting where I just need to set this to false, and everything else is same. Here the output, the second last layer has the size 1024, and I am just adding 10. I'm just adding changing the output size here. Same for Google Net and same for RESTnet as well. RESTnet 18. So RESTnet has also four types of types of architecture: 18, 31, 50, and 152. So I chose the least one because it is a very lengthy model, and it is very dense, so it will take a lot of time. AlexNet 2. AlexNet is the smallest among them, and the code is exactly the same. So you can see I actually trained AlexNet and I couldn't evaluate it. So let me do one thing. Okay, so this is training. So one epoch is now done. So it will take a few moments to get trained. So I'll wait for some time, and let's see if it's getting trained or not. So AlexNet has trained, and it has given better performance than the vanilla CNN. So these are the benchmarked CNN. So I'll wait for some time. Let's see to see if it is giving, if it is running fast. Otherwise, I will let you guys run this on your own on your side, and report me the accuracies and all the accuracies that you got for different models in a graph, so that you can compare between these four models, which one is better classifying this Cypher 10 dataset. Okay, I guess this will take a while, and I want to wait to guys for this one, because I would request everyone of you to please run this and get the results. It's a very nice way to sort of utilizing what is there for us, and we can utilize it without for free, and we can just take these models, because people spend years developing these models and training. So we don't have to do that. We get the models out of the box, and we just retrain it for our purpose. So if you have any task in your hand which is might not be Cypher 10, it might be different. You can just download these models and update the front layers accordingly, and sort of play around with it, and train your the model for your own task. So if you get stuck in any code, suppose you want to try a new data set that is not fitting in this code, so you can always Google things up, and you can always sort of find new a solution to that, and sort of update all these things. So ma'am has shared the quiz. I think it's 9:40 now, so I think it's 15 minutes or 20 minutes past the session. So I would request ma'am to so I think I can close the session now from my side, and the quiz will go on. And yeah, the second epoch has done. So I think it is taking 2 minutes for epochs, and it will take more 15 minutes to run. So once the quiz is complete, you can come and check what is the evaluation, what is the accuracy that VA16 got. And now I'll request ma'am to address uh, about the quiz and the session end.
So inside you can continue the session just before your 15 or 20 minutes. I have posted the quiz link.
Okay.
If your session is continuous, you can continue. That means before that, I want to give the quiz link before 15 or 20 minutes.
Yeah, no, actually, I mean, this code is taking. So what I've left in my session is that I just need to run this code, and show the results that it is getting better while we're using pre-trained better models that I taught earlier today. So since it is taking a lot of time to run, so I don't think just waiting for this to give results will not be fair. So if you want, you can conduct the quiz, and after 15 minutes, this result, so this code will run, and the results can be seen in the notebook itself.
Okay, sir. Okay.
So I mean, the quiz will be offline, and should the meeting should go on, or should I stop the recording now? Hello, ma'am. Hello, ma'am. Should I stop the screen recording? Quiz.
Okay, sir.
Okay. So yeah, I am ending this session, and I'll be hoping that everyone of you see the results that this code is getting. You can see it in your notebook as well. So until then, thank you everyone for joining, and be with me in this very long 3 point round.
Thank you, Swain, sir, for your informative and long session.
Yeah. And thank you. I'm stopping the share, and we'll meet tomorrow for discussing RNNs and LSTMs, which is essential for text data that we see in today's life.
Thank you.